So basically, Hesenberg uncertainty principle states that we cannot determine position of the particle or its momentum, infinitely precisely. So this is what we have here, basically. Let's see if we can zoom in. And here's the marker. So delta P times delta X is more than H. More than H. H is Planck's constant. There's a certain number, there's like, I think H over 4 pi or H over 2 pi, but we're not going to go into that. It's just, you understand that it's more than 10 to the negative 34 in the order of the magnitude. You can also transform it into delta E times delta T, more than H. So these are the same thing. So let me see if I can box this thing like that and like that. Okay, so those are the same thing. Now, in order to understand this, we have to look at the earliest development of movies, animations. So if I can switch to something else, let's see, we can switch to the horse. Where's the horse? This horse. So we're going to switch to the horse. No. Okay. Why does it want to switch to the horse? Oh, there it is. Okay, can you guys see this picture? Do you see the horses? No. Oh, that sucks. Okay, so that means I have to stop presenting because I don't know why it's not sharing that with you. So let's see, I'm going to stop this thing and I have to start presenting something else. Horses. Here you go. So you should be able to see the horses now. Yes. Okay. So if you ever studied the earliest like a little bit about movies, right? So the first movie basically was made by a person who took pictures. So I guess that's the name of the person who took pictures of the running horse. So basically, the running horse, a straight line. They placed every whatever 10 meters, 5 meters cameras, and these cameras were timed, so they would be taking pictures as the horse would pass by. So you should realize, I'm sure you realize these pictures, they show that the horse is running, but it's running in your mind. In the picture, the horse is not running. The picture is a still picture. It's just our mind says that, oh, the horse must be running. The horse cannot maintain this position. It cannot be hovering above the ground like so. So it must be in motion. And then we instinctively connect all these images into one movie or animation or moving pictures, right? Now, and then the result is going to be somewhat like GIF, please. I saw that before. Yeah, there it is. So that's what we see. And the first movie basically will be pictures of the horse, still images of the horse, taped inside of a cylinder, and the cylinder would be rotating and the pictures will be moving, but you peek into this cylinder from one perspective and you can only see one frame at a time. And as the cylinder rotates, right, you will see that all these pictures are moving, and then combined together they create the sensation that this thing is moving. Okay, so that's the funny animation. Okay, we know that the picture in each picture the horse is not moving, right? So this one. Yeah, so the various kind of pictures. Okay, so that's the point. Now let's try to use this to understand. Um, oh, this is awesome. To understand uncertainty principle. Okay, so now I'm gonna stop sharing that and I'm gonna switch back to the whiteboard. Technology at its finest. Okay, so going back to this. So let's try to understand why Heisenberg uncertainty principle is important. Like, first of all, like what is it? The horse is running. When the horse is running, we're looking at the horse, but we can't just look at the horse because our eyes cannot reach out and kind of touch the horse and see, oh, there it is right now, and then later it's there. So we're shooting light at the horse, and light bounces off the horse, and then we see that light. So in a way, we're kind of feeling the horse, but not like physically or with like eyes or hands. We're feeling it with the light. So the moment you and for the horse, obviously, or any microscopic object, light does not have like any significant effect on its position or its velocity. The horse will be running no matter how much light you shine on it at the same speed, and it will be in the same position. Um, but if you do so with particles, then you have a different story. So particles in microscopic world are very tiny. They have really small masses. So, which means that if you have, say, an electron, suppose we suspect that electron is somewhere here, and suppose we have the flow of electrons, we expect all of them to move generally in this direction. Now we're trying to pinpoint position of this electron. We can't find it, just, there's no way to look for it, uh, unless we shine a piece of light, a piece of a photon. So we shoot a photon into it. If we're lucky, the photon collides, bounces off, and then we see, oh, electron was there a moment ago. Okay, now we know from Compton scattering that electron will interact with the photon and then it will bounce off. So basically, electron will be then going somewhat this way, taking part of the momentum away from the photon. So now we no longer know which way it is moving precisely. And we don't know again also where the electron is. So we know that where it was here, so more or less precisely, but we don't know how fast it's moving after it interacted with this thing. In order to find out how fast it was moving after interacted, we have to look for it somewhere in this area, and that makes it really uncertain. So let's see if we can do this. So electron can be somewhere here in this cone, basically, right? In this specific case. So let's say we're looking here and we can't find it. And we'll look everywhere and then, okay, we'll find it somewhere around here. So now we expect it to be somewhere like here, but then it's over here. So our uncertainty in the position has grown to a large number compared to uncertainty in the momentum. So we try to find the position, we affect the momentum. We try to find the momentum, we affect the position. And that's the idea behind uncertainty principle. You cannot find the particle as precisely as you can find its momentum. So besides, since all electrons are the same, what if we detected a different electron here, and our electron that we actually kind of detected here went away somewhere else? So how do we know this is the same electron? So that becomes an issue as well. Any questions about this? No questions, right? No questions. Okay, so let's try to understand the second equation, delta E times delta P. So again, it's the same thing, but we can understand kind of different slice of this concept. So let's see. In this case, uncertainty of the time and energy, right? They cannot be less than h. They have to be more than h. One of the misconceptions about this is that, oh, we don't know how precisely, time is determined or how precisely position is determined. The thing is that h is quite small. If h is quite small, then obviously we can determine with this kind of level of precision, right? The point is we cannot determine both of them with the same level of precision. So if one is more precise, the other will be less precise. So suppose we're looking at the process that takes a very short interval, short amount of time. So let's say it's about 10 to the negative 23 of a second. There's some nuclear processes that take a very short amount of time. So if delta t is about 10 to the negative 23 seconds, then delta E, according to uncertainty principle, will be about 10 to the negative 11 joules. Now, for us, it doesn't matter, right? If someone, shining a light on you with a flashlight, you're not gonna be pushed away by the light, right? Your position, your velocity will not be affected at all. If we're looking at the microscopic world, it's a different picture. A tiny amount of energy is enough to push the particles around. So in this case, we're looking at the slice of time, which is 10 to the negative 23 of a second. The energy uncertainty is 10 to the negative 11 joules. If you remember, visible light is about 10 to the negative 19 of a joule, roughly. X-rays will be around roughly 10 to the negative 15, 10 to the negative 14 joules. So we're talking about basically like almost like gamma rays. So what's happening here? Imagine you have a microscope and you're using this microscope somewhere like in deep space in the vacuum. Or it doesn't have to be in space. You can do it in the lab. So you create a really good vacuum. And you want to check if it's a really good vacuum by using this special microscope. So you're zooming in, and you're looking at the chamber, which is dark. That means you're not shining any light into it. There's another aspect of this. So a certain principle is that you're looking at in a black box. What's inside a black box? You don't know. How can you know what's inside a black box? Well, you have to shine the light. And once you shine the light inside of it, it's no longer a black box. Or another way, let's say you are in a dark room, completely dark room. Now you want to know what's in that dark room. What do? You turn a flashlight. You turn the light. It's no longer a dark room, which means you affected the reality. You changed the reality by trying to look at it. And in the microscopic world, it's much more like pronounced. So we're using this microscope. We're sure we create a really good vacuum inside this vacuum chamber. We zoom in, zoom in, zoom in. We don't see anything. So we're happy. Now, let's say this microscope also allows you to kind of stretch time. So we're trying to now to look at this vacuum at the shorter intervals of time. So you look at it at a short interval of time, You don't see anything. You don't see anything, and then you're reaching this 10 to the negative 19th of a second, 10 to the 20th of a second. All of a sudden, you see these particles emerging, and you start wondering how come you create this very good vacuum. It's empty space. Nothing is supposed to be there, and all of a sudden, as your time scale becomes shorter and shorter, you see these particles emerging. And at a certain point, you will see, basically, if you're taking a picture of this vacuum, of this emptiness, at a shorter and shorter interval of time, you will see more and more particles emerging from nothingness. And they will have more energy. They can do more stuff. And basically, that's called virtual particles. So this could be basically a virtual particle. A virtual particle. And the shorter the interval time, the more likely it will appear, and the more energy and the more mass it will have. And is it real? Because right now we're just doing thought experiment, right? Is it real? It is real, very much real. And one of the manifestations, macroscopic manifestations of this is that so-called Casimir force. Let's see, we can right here. I think it's called Casimir force. So Casimir force is not gravitational, is not nuclear. So what is it? Let me see. Let's see, Casimir force. Casimir effect, or we can call it Casimir force. So basically, it's the force from nothing. And basically, if you have two plates, let me draw it here. Two plates separated by a very small distance between them in a complete vacuum. Again, the vacuum we create, in a really good vacuum we create in this chamber. As you bring them closer and closer, at a certain point they will start attracting each other. And why? Because as you make the gap smaller and smaller between the plates, you get more and more forces pushing this from outside. So basically, you will have force coming from here and force coming from here, and not enough force coming from inside. So force from inside will not be enough. Meaning that the plates will basically come together unless you create resistance force, external resistance force. So this is Casimir effect. It has been measured. It exists. It was predicted by, I suppose, Casimir. I have not read about him, so I can't really tell you. Here it says Henry Casimir predicted this 70 years ago. And this force was measured by NASA, as far as I remember. So this force is real, and it was even suggested to be used to propel like spacecrafts. Not sure if you can do it, but you know, it's something unusual. So how can we explain these things? As delta x becomes smaller and smaller, the space between the plates becomes smaller, and you have fewer particles, virtual particles, created inside that volume. While outside, you have a larger number of virtual particles, so overall they create net pressure inward onto the plate. So the plates will be then attracted to each other. So that's Casimir force. Okay, are there any questions? Do we have a connection? Do we have internet?
You're back now. You froze for a second.
Oh, just for a second or for like long second?
For like a long second.
Oh, you see, this is the uncertainty principle because my position was precise, but delta t was like stretched out, right? There you go. That's uncertainty principle in the microscopic world. So what did you miss then? I froze, meaning that the video or the sound as well?
The sound as well.
Oh, okay. So you missed a lot of stuff then. So when did I freeze?
You said something about Casimir.
Okay, so let me go back. You guys see the slide though?
Yes.
You see this stuff?
Yes.
Okay, good. So Casimir force was predicted by Henry Casimir. I just looked it up about 50 years ago. And this force was measured by by NASA scientists uh, in early 2000s. So basically, it's a macroscopic manifestation of microscopic world. So what's happening here? We have two plates, and as you bring them closer and closer, as you reduce the gap between them, and these plates are in the vacuum. So you put it in the vacuum chamber. Nothing is outside of these things. So you can't claim there's a attraction, electrostatic attraction. There's no tension forces. There's no air pressure. Nothing like that. Excuse me. And there's no gravitational force. I mean, there is gravitational force, but it's not enough to attract them. So what happens is that these plates, as you bring them closer and closer, they will start attracting each other. And this force of attraction between them is inversely proportional to, I think, displacement and distance to the fourth power. So it's not inverse square law, it's not static, electrostatic, it's not gravitational. It's not nuclear. So then what is it? Well, as you reduce the gap between the plates, you reduce the amount of virtual particles created in that volume. Outside of the plates, you have more virtual particles created, and they create net pressure and push the plates together. So this force has been measured, and it was confirmed that it's inversely proportional to the distance to the fourth power. So if they're a certain distance and you bring them 2 times closer, the force between them will be 16 times stronger. Okay, did you guys receive that information? Am I frozen again?
No, that was good.
You're good? Okay. Okay, I think I'm tired of talking. If you have any questions, ask. If not, I'm gonna retire.
I have one.
Go ahead.
When you create the virtual particles, do they stay? Or
No.
do they disappear again?
Yes, they have to disappear because as soon as you stretch the time to longer, so as delta t becomes longer, right? The delta E becomes small. So if we have, let's say we observe this for delta T 1 second, then delta E obviously is like joules, which means virtually non-existent. So as you stretch the amount of time, the particles will disappear. So what's happening, how can we imagine this? What's happening is in the nothingness, you have 2 particles. Let's say you have, let's start with a photon. So let's say, so first you have nothing, then you have a photon. A photon will have, depending on the delta T, will have really huge amount of energy, enough to create 2 particles, for example, right? 2 particles. So it will create 2 particles, which will be 1 electron, the other will be a positron. Those particles will be created conservation of momentum, energy, everything is good. Then they will come together and they annihilate. So they create a photon again, a virtual photon, maybe two photons, I don't know. And this photon will then disappear into nothingness again. So unless you have the really short interval of time, you won't see this happening. Make sense?
Yes.
So they appear and disappear quite quickly. So in order to observe them, you have to have ability to, like, like those, if you watch those YouTube channels where they shoot things with a really fast camera, right? Certain things you cannot see unless you have, like, you're running like 100,000 frames per second. You will never see that. So that's kind of the same thing. Okay, any other questions?
I guess we're good.
You good? All right then. So let me check the time. 1 second.
Also, some of us have the AP English exam tomorrow. Should we just?
Yeah, it's fine. I just take your exam. Don't worry about it. Whatever I present, I'll try to record. So I think I'm recording this today now, right? Oh, I'm still recording this. Oh my God. Okay, this will all be on YouTube video, unless I trim it down. Okay, I'm gonna stop.